Hello, in this video we're going to work out what happens in an elastic collision where the kinetic energy is conserved. So here's a sketch that's going to lead us through our derivation. We'll have two objects and we'll let them have different masses. So we'll have an m1 with some v initial 1 and we'll have m2 with v initial 2. We'll assume that the velocities do let them actually run into each other. And after the collision, we're going to have different velocities. We'll have some, let's call it v final 1. Or let's just call it v1, actually, to cut down on the number of subscripts we'll need. And then object 2 with mass 2 will have velocity v2. And maybe these are negative. Maybe one of them's gotten bounced back to the left. Okay? In any case, we will stick to just one dimension like we've been doing, so everything moves left or right. Assuming that we know the masses and we know the initial velocities, we're going to be able to calculate both of the final velocities without needing to know either of them ahead of time. And the reason we can find two unknown values is because we're going to have two equations. We have conservation of momentum as equation number 1. So P initial is equal to P final. And we also have conservation of kinetic energy. K initial is equal to K final because it's an elastic collision. That's only true for elastic collisions. Now this is good from a calculating things point of view because we have more information. This is bad from a physics student's point of view because you have more calculations. Well, the idea here is we're going to work through this derivation together in this video so that you don't have to grind through the setup every time you want to solve a problem with kinetic energy. Now, I know there's a temptation just to jump ahead to the end, get the equation, and then you're happy. That's not really ultimately in your best interest. Following along here, you'll get to see how we can put these equations together. Maybe I'll show you a problem-solving trick you hadn't thought of. In fact, if you want to pause now and try and set it up on your own, that's actually great. Don't spend too much time trying to solve it because my hunch is that your first approach will be an inefficient one. Just trying to substitute one equation into the other is not a very good way to do this. Alright, so the way I would do it is I would write down both equations to start out with. That's sort of an inevitable first step. So conservation of momentum tells us that m1 times v initial 1 plus m2 times v initial 2 is equal to m1 v1 plus m2 v2. And conservation of kinetic energy gives us a very similar looking equation, except it's going to have a half and it's going to have velocity squared. So the first term would be 1/2 m1 v initial 1 squared plus 1/2 m2 v initial 2 squared is equal to the final state, which is 1/2 m1 v1 squared plus 1/2 m2 v2 squared. Now an obvious thing to do at this point is to cancel out all those 1/2s because they show up in every term. So now we have two equations that look very similar. The difference is one of them just has v's to the first power and the other one is v squared. Okay, now like I was saying before, at this point your first approach would probably be to try and substitute one into the other, and that quickly becomes absolutely horrible because you have all these squares, the thing's quadratic. You could in principle do it, but I've never actually seen anyone work it through all the way, so I guess now you have your challenge. Nonetheless, there is actually a much easier way to do this, which is what I want to show you in this video. First thing we're going to do is rewrite our equations. Okay, so we'll take this first equation here, and let's try and sort all the 1's and all the 2's. So our first equation will become m1 v initial 1, and then I want this term, so minus m1 v1. And then on the other side of the equation, we'll have m2 v2 minus m2 v initial 2. I can then notice that, hey, I have m1 in both of these terms, and I have m2 in both of those terms. I can factor each of those out. So I get m1 times v initial 1 minus v1. And on the right-hand side, I have m2 times v2 minus v initial 2. All right, so I'm going to call this equation 1. And I'm going to refer to equation 1 a few more times. We can do the same thing with kinetic energy. That will be our equation 2. So we'll start with m1 times v initial 1 squared. And then I want to subtract from that over here m1 v1 squared. And then on the other side I want the 2. So I want m2 v2 squared minus m2 v initial 2 squared. Notice it's basically the same equation, just with all the velocities squared. And again, I'm going to factor out the masses. So I've got m1 times the quantity v initial 1 squared minus v1 squared is equal to m2 times v2 squared minus v initial 2 squared. And that will be equation 2. Now here's where the trick comes in. In fact, let's put this in another color because this is the handy part. So since it's true that a squared minus b squared is equal to a plus b times a minus b, presumably it's something you saw in high school, though maybe you've forgotten about it since this is just difference of squares. So this is always true. Since that's true, equation number 2 is going to become m1 times, well, look, each of these are difference of squares. So it becomes m1 times v initial 1 plus v1 times v initial 1 minus v1. And then on the right hand side, we get v2 minus v initial 2 times v2 plus v initial 2. And let's take that equation and divide it by equation number 1, because equation 1 is m v1 or v initial 1 minus v1, and hey, we have that term here. Likewise, we have a term that we could cancel out on the right hand side. All right, so if we do that, we're left with just the added term. So we have m1 v initial 1 plus v1 is equal to m2 v2 plus v initial 2. Oh, and actually I should have canceled out the m1s. Actually, let me write out that intermediate step. I think I've skipped one step too many right there. So let's just write out that division. So we'll have equation 2, which says m1 v initial 1 plus v1 times v initial 1 minus v1 is equal to m2 v2 minus v initial 2, v2 plus v initial 2, and then we're going to divide both sides by equation 1. So that's m1 v initial 1 minus v1, and on the right we have m2 v2, v2 minus v initial 2. All right, and so the subtraction terms cancel out and the mass terms cancel out. And so we're just left with some velocities equaling each other. Let's write that down clean here on the next slide. So we have v initial 1 plus v1 is equal to v2 plus v initial 2. So we have a relationship between our velocities, which lets us eliminate one of our unknown variables. So let's say we want to get rid of unknown variable v2, final velocity 2. So that would be equal to v initial 1 plus v1 minus v initial 2. And we want to plug that back into one of our earlier equations. Equation number 1 is easier to work with because the velocities aren't squared, so we'll plug it back into equation number 1. So that tells us that we have m times v initial 1 minus v1 is equal to m2, this should be m1, is equal to m2 times v2, which we now know is v initial 1 plus v1 minus v initial 2, all that minus v initial 2. So this stuff right here, that's v2, and we've made the substitution. So we've removed v2 from this equation, which means that now, after a little bit of rearranging, we can solve for v1. On the left-hand side, we have m1 times v initial 1 minus m1 times v1. And on the right-hand side, we'll have m2 times v initial 1 plus m2 times v1. And then we have two of these, so minus 2 m2 times v initial 2. We need to get these v1s together on the same side of the equation. So let's go put them over here on the left. So we'd have, I want to move, well, actually they'd both be negative, so we'll put them on the right. So we'd have m1 v1 plus m2 v2, and then we want to put everything else on the left, and then I'm flipping my equal sign just to be difficult. So on the other side of the equation, we have m1 v initial 1 minus m2 v initial 1 from over here, and then finally plus 2 m2 v initial 2. And so finally we get an answer here. v1 is equal to, clean this up a little bit, m1 minus m2, the quantity, times v initial 1, plus 2 m2 times v initial 2, divided by m1 plus m2. All right, that took a little while. I think that's worth drawing a box. Not because it's some fundamental equation of physics, but because, hey, after that I want a box. All right, and you say, oh no, we're only halfway done. Actually, there's a very nice trick here. Everything's symmetric. It doesn't really matter which one we called 1 and which one we called 2. So to get v2, all we have to do is swap the 1 and the 2's, and that'll give us v2. So v2 is equal to m2 minus m1 v initial 2 plus 2 m1 v initial 1 divided by m2 plus m1. And you might want to rewrite it to make it look a little bit more like the top equation, but that's all you really had to do to get it. In fact, that right there tells you there's going to be some sort of symmetry in your answers. That doesn't mean that they're the same number, but there's symmetry in how you calculate v1 and how you calculate v2. All right, so let's try that example we've been using for our kinds of collisions. We'll try that here with the elastic collisions. So just as a reminder, our setup was we had a ball with mass m moving with velocity v initial. It runs into a second ball with the same mass m that's at rest. Now after the collision, we're going to have the balls moving away. We need to have some overall momentum to the right. If these numbers come out negative, that means that one of them ended up bouncing back to the left. That's possible. But let's see what we actually get for these two velocities. So a quick reminder, since it was on the previous slide, v1 is going to be equal to m1 minus m2 on m1 plus m2 times v initial 1 plus 2m2 on m1 plus m2 times v initial 2. I'm just rewriting it a slightly different way to show you how we get these ratios involving the mass in terms of the initial velocities. Likewise, we'll have an equation for v2, which tells us that v2 is equal to 2m1 on m1 plus m2 v initial 1 plus m2 minus m1 on m1 plus m2 v initial 2. Notice that these terms are in different order, so one of these is going to be negative of the other. What do we get in our case? Well, v1 is going to be equal to the difference of the masses, which is actually 0, plus here we're going to have 2m divided by, well, 2m times v initial 2, which is v initial 2. So v1 is equal to v initial 2, which is actually 0, right? This is the initial velocity of the second ball, which is 0. So it tells us actually that this first one stops. And what about the other one? Well, maybe you can guess what's going to happen, but let's just work it out. So we'll get 2m divided by 2m times v initial 1 plus 0 is equal to v initial 1, which is just v initial. So in fact, what happens is we start out with one ball moving and the other one at rest, and after the collision, this first one's at rest and the other one is moving. Okay? And so that's actually a neat result of elastic collisions. This is because the masses were the same. If the masses were different, then it may be that both end up moving afterwards. You'd have to plug that into your equation to see exactly what would happen in each case. But suppose you have, I dropped my pen. Suppose you have a situation where we have two balls with equal masses, say billiard balls on a pool table. Billiard balls don't smash together, they don't crumble or deform when they hit each other, so they basically undergo an elastic collision, pretty close to elastic collision. So if you have one billiard ball hit the other one head on, what happens is that one stops, this would be your cue ball, and the other one goes flying. Now it's possible in billiards to have both balls move after the collision. Think about under what circumstances that happens. It's not because the balls have different masses, it's because sometimes in billiards you don't have a head-on collision. If we hit not head-on, then what will happen is that one of these is going to end up in our after picture. I guess our cue ball here is going to end up heading off in that direction, and their target ball will end up moving in this direction, because that's actually a two-dimensional collision. Here what we've set up, and we've drawn our boxes around, is for one-dimensional elastic collisions. That was our initial setup way back here when we drew our picture. If our setup is two-dimensional, you have to do this for each component. So it's really the technique here that's important more so than our answer. Nonetheless, in this particular case, you don't have to derive it again because we already did. Okay. So I'll see you in the next video.